everyone. This is the bi-weekly libhal meeting. Let's get started. It is March 31st, 2026. And for the agenda today, there's not too much for today. I'm going to go over quite a few updates to async context. Also wanted to bring up one thing that kind of popped into it became relevant last week. Basically, we had a student who was using libhal, and they have an x86, an Intel macOS device. Basically, Mac and ARM are moving away from x86, so they're not really supporting any versions of GCC for it. And the other sources that I would normally get for this don't really exist. And because the x86 line of laptops, and I have to look around to see if there's other devices we could use. There might be some other more modern Mac devices, but I'm going to assume that there really isn't. So you may wonder, well, why not just simply, build the tool chain yourself? Then we wouldn't have to worry about that. Well, that just involves us getting the hardware. And I have a feeling that in the next couple of years, since Mac is moving completely over to ARM, I don't really suspect that we will have good hardware to work with. And get enough support to make building those older versions of the tool chains for Mac work. So once we move over to GCC 15, Mac x86 support is probably going to be dropped, which is unfortunate. Let's go over a few more things that I didn't put inside the agenda. We're making good progress on USB, which is really cool. And I think those are kind of the big things. There's been a lot of other work being done in the background, but for the most part, these are like the bigger items. All right, so let's go into async context. This is nearly done. I think I have a few more things I want to finish up with this, and then I'll merge this into v5, up the version number, and then start getting through all of that. I have been making some progress on v5, and actually before I go any further, I'll say one more thing. We are adding in support for I2C memory map. The memory map target. The idea is that rather than having APIs for interacting with I2C, we just simply provide access to and from the memory map, and then the driver handles performing all of the I2C transactions to make sure all the information is sent back and forth. It's cool stuff. Maybe in the future we might have a more generic version of this just for any and all devices versus having it based on like I2C specifically. Not sure where the line should be drawn, which is why we're not going to go into too much detail about it today. All right, so let's go into async context. I made a number of pretty significant changes to async context. Before, there used to be a virtual API. It used to be an abstract class with a pure virtual function. I have since removed the doSchedule API and replaced it with, and not really fully replaced, but replaced it with an Unblock API and an Unblock listener. One thing to kind of bring up is that about, I think 3 weeks ago, I looked back at async context and tried making some schedulers. And I made some schedulers, or I just made one, and I was not happy with what I had. I realized that one of the things that I designed async context with back in the day was this idea that there was an explicit, let me see if I have another API for this. Yeah, I do, or another slide for this. So why did I make this change? Why no virtual doSchedule? Well, the only way for doSchedule to work correctly is if your custom scheduler, whatever you built, also creates its own context type. So the thing is, if I have some round robin scheduler, then the doSchedule function needs to know how to interact with that scheduler. Therefore, I need to make a context specifically built for the round robin scheduler. And what ends up happening is then having to pass the scheduler in by reference so that this function, or this class, when you call its virtual API, knows how to peek into the memory, find the scheduler, and then add itself onto that scheduler's queue. Same thing with the RTOS scheduler. This one, I just came up with a couple of random names. These aren't really anything meaningful, but I just wanted to kind of show that if you have these different types of schedulers, each one of them will need its own context. Now, luckily, you can pass those contexts to any coroutine accepting, any context accepting function. That's not a problem. Polymorphism works just fine there. The bigger issue was that it felt like none of the contexts were reusable. And if I wanted them to be reusable, they mostly had to be mix-ins. And then I had to kind of stop and think about what it was that I was doing. And this is just me re-saying that like this felt very much like the initial version of context, where you had to pass in a required scheduler so that the context knew how to schedule things. Which all this did was push that into becoming more implicit. Sorry for the misspelling here. Basically, this made it an implicit requirement that you organize your code in such a way. Whereas before, at least it was more explicit. So I actually really did not like the fact that we had this implicit requirement for a scheduler to be passed into each context. So at some point, I had to question the purpose of the transition handler. The previous API would tell you anytime the state of the context changed. But then I realized that's kind of silly, because what is the benefit of making that indirect call, making that change when you call resume, and it basically resumes the asynchronous function calls and just synchronously runs through everything else until it finds a suspension point. Once it finds a suspension point, it returns however deep it was right back to this point here. And then you can check its state. And when I realized that I could just check its state right afterwards, I started to no longer see the value in having a transition handler. I think I came up with it originally because I thought the amount of data that I want to pass over to it would be significant enough to the point where I wouldn't want to compose it into the context. I would want to give it to the scheduler, and the scheduler can drop whatever information it doesn't want to keep. That was the original inspiration for the transition handler. Any bits of information that the scheduler did not care for, it could drop and ignore, and it would not use up any more memory. It only temporarily used memory on the stack in order to pass those values down. Once it ignored them, those all got wiped out. That was the plan. But then I realized it's real simple to just call resume and then just check the state afterwards. Now, with the transition handler, if you wanted to block by time, you needed to provide an actual time. The time got forgotten if you did not take it at the moment of the transition handler being called. This made me decide on a few things. I tried to remove some things around. Basically, context now is one word past a cache line, which is unfortunate. But I decided to put the sleep value into the context. You'll see this in the next APIs. But the thing that I realized is after I got resume to work and realized that the state checking can happen right afterwards, I realized there's only one thing that I actually need to know the moment it happens. You can get around this if you don't care about it. You can poll. But if you want to get away from polling and you want that performance, you need to have some sort of unblock listener. You need to have something that when an interrupt says, hey, we're done, can just basically say, hey, we can unblock this thing. That was what I was able to kind of take to the transition handler and boil it down into simply the unblock handler. So let me show you some of the new APIs that are now inside of async context. Don't worry about some of these things that got replaced. If you weren't paying too much attention to what the things were, doesn't really matter. Basic context is basically doing what in-place context does, except in-place context doesn't have a virtual API anymore, so now it's a lot easier to implement. Since now context is a concrete type, all the inheritance problems that we got with polymorphs with virtual APIs are completely gone now. We'd have no more vtables, so we have nothing to worry about. Your unblock handler has a vtable, but yeah, that doesn't really matter too much. Oh, I did not add those APIs in here. I should have. It comes up next. But some of the new APIs, now when you have a context, you can actually ask it for how much sleep time it has and or give you back its sleep duration, which is, I changed it to be microseconds and to be a U32 value. The purpose of this, and actually since this is a U32 value, it actually might be a cache line on x86 device. I'm sorry, on 64 devices that have 64 bytes of cache line size and have 64 bits for the register size, should actually fit. Anyway, I reduced the resolution of the sleep time just because nanoseconds is something that's hard for any scheduler to manage in terms of hitting that requirement. It doesn't matter if it's hit, but it's just such a high resolution that I just don't think it's going to be useful in most cases. especially when you're doing asynchronous sleeping. You're not expected to be too high precision with this. 32 bits gets you, I think, if I remember correctly, it's either 4 hours or 2 hours, but I think that's a good enough amount. And if any code needs to sleep longer than that, then that code can loop the amount of durations that needs to sleep. We also provide a get blocker. So whenever context gets blocked by synchronization, which we'll talk about later, you can get information. You can basically get which context is currently blocking that one. If you want to, you could resume that context instead of resuming your current one. If you want to just pull it. The basic context before used to have the sync wait function. Now the sync wait function has been added into context itself. It will basically do the work of scheduling and polling the context synchronous operations. And anytime it needs to sleep, it will use the function that you passed in. So you just hand it a delay function, and it'll delay that. It'll sleep for that duration of time until it's finished. And I don't remember if I've spoken about this at all in the past, but one thing I wanted to make clear, and I've got to remove the context here. We have a cancel function. Async context is, as far as I've designed it, as far as I know, cancellation safe. At any point, you should be able to cancel your code. If some code behaves badly because it's canceled, it means that the code was not cancel safe. And I don't remember if I've spoken about this in the previous meetings, but I'll say this again. Cancellation safety is the same as exception safety. You should consider when you write your code you should utilize RAII, use destructors, to undo any work that has occurred. That way, in between call wait statements, if the code or the system decides to clean up, it can just destroy all those things. Yeah, that's pretty much that. All right, so on top of things, I've also added in a function that's a very basic scheduler called run until done. This allows you, let's say you were building up some code for the rover, for a robot of some sort or anything, and you just had like a set of tasks. Well, you can basically give your list of contexts that had the tasks on them to the run until done scheduler, and it'll do just that. If these tasks never finish, then run until done will just continually schedule until they're all done. It has the logic to manage sleeping for the shortest duration of time until the next context is available. That's what this API here is doing. And actually, I'll go through what's happening here. So the first thing we do is we actually create a clock. The global static clocks with their now static function isn't really useful here because we need to be able to some clocks, you may have a clock that needs to be dynamically created or created at runtime, not statically created. But we do have a chrono clock adapter that you can pass in your chrono clock in order to create a clock. The clock is necessary in order to give a start time for all of the sleep durations that occur. This allows the code, the run until done, to, whenever it sees a context or a context that is blocked by time, it can basically add the current block time plus the now time, and then get a future deadline in which it should continue, when it should resume that particular context. So you pass in a clock so it knows what the time is. You pass in a function, some callable, that you can pass a wake time into. It's a sleep duration API. I just put auto here to make it easier for myself. And in this case, this is not exactly what you would do, but a very lazy way to go about this would be to pass this into sleep until, and then you just put in the wake time into that. And then I'll sleep until it's done, until it's ready to wake back up. Then lastly, you put in the list of contexts. Now, I actually had one of the students bring this up, that like having to pass in the context is a little bit confusing for schedulers. That is kind of true. You could pass in the tasks, the futures directly into this. I just haven't written the run until done to manage that. Another thing that I'd like to do is if you pass in a list of futures with their own return types, there would be a return value from this, where the return value would be a tuple of whatever values you expected to get from all the futures. I believe this is how when all, I could be wrong, but I believe this is how the sender when all works for senders and receivers. I know one of the senders and receivers in C++ 26 comes with a response that is a tuple of all your results. So yeah. Another cool thing about this is that this doesn't utilize any heap memory, no dynamic allocation. It just utilizes stack memory, and it uses 2 times n pointers for each context. So yeah, it basically, actually, I think I might be wrong. I think I might be wrong about that. It might actually be 3 pointers, except for 2. The reason why I say 2 here is that we need to keep the time point where each context needs to wake up at, and then also the pointer to the context. And this is just so that we can iterate through an array and round robin around. And that's pretty much that. This very basic scheduler, very efficient, very tiny scheduler. If you look at the code, you'll be able to very easily understand what's kind of going on. So that's a little move that we added in. A long time coming, and now that I've simplified context quite a bit, it makes it much easier to write schedulers because they're very generic now. One thing before I go further, I don't think I've spoken about this, but we also have I talked about in-place context, just so everyone else knows. Whenever you create a context, it has no stack memory. You have to provide it stack memory. You have to provide it a span of your stack words. In this case, we use the unsigned pointer type, basically whatever the size of a pointer is, but as an integer for that. In this case, you can specify how many bytes you want, or sorry, how many stack words you want. In this case, it's 512 for all 3 of these. On a 32-bit system, it's 512 times 4 to give you the actual number of bytes that are allocated. Very easy way to just get some memory and start using it. All right, so something I haven't talked about in a while, actually I don't think at all, is how to go about blocking and unblocking. I think even the docs are missing this, so I want to kind of talk about it here, and at some point I plan to update the docs to include this. So when you're writing a coroutine, there's only one blocking state that does not require you to pull it, and that is block by time. So anytime you write in co-await 50 milliseconds, the scheduler is required to defer execution of your coroutine until that duration of time has elapsed. It has to wait until that time. Now, it can wait a lot longer. It could actually potentially never reschedule you. That's kind of degenerate behavior, but it could never reschedule you. That could be because some other code is taking up all the time. The only requirement for block by time is that you do not reschedule it or do not resume it until the time has elapsed. But however long that is after it's elapsed can be whenever. Block by I/O. If you have some code that's performing some I/O and it can run synchronously, just before I go into the other details, it should just return normally using the normal return keyword. It should not use co-return, it should not use co-await, it shouldn't do any of that stuff. It should just simply return. If you're going to toggle a bit for a GPIO or read a bit off a GPIO, it should be synchronous. If you're doing some bit bang I2C, you probably have no time to wait, so you should just kind of stay synchronous, or maybe you could suspend. I don't know, but I think by default you'll just run this synchronously. And let's say you're going to grab some data from an ADC, but the ADC is actually continuously sampling. So if you just read the register out for the ADC, you'll automatically get what the current value for the ADC is, and then you can just move on from there. You don't need to, start the sampling, then wait for the interrupt for the sampling to return before you can gather the data. Now, on the flip side, and on the probably more likely side, for quite a few different things, you're going to have an interrupt that will tell you when something is finished. So, for example, if you're doing some sort of, who knows what you're doing, SPI, UR, I2C, probably not CAN, maybe I can too. You'll set up some hardware. You might set up some DMA transfer, and maybe it can take in a callable. In that callable, you'll take the context and you will unblock it. The idea is that the interrupt will perform the unblock, and don't worry, just to repeat this, unblock is no except, so we'll not throw an exception, and it is part of the documentation that the implementer of the unblock listener should not throw and should simply only set values, put something on a queue, put something somewhere in such a way that's non-blocking, just so that the rest of the code can perform what it needs to do. Once it's all set up, you basically start waiting. So you do while hardware is busy, block by I/O. If you get to this point and before you even hit this line here and it's already unblocked you, then you just pass through, no unblocking, proceed as normal. But if the hardware is busy, you block by I/O. Here's the thing about block by I/O. The code, the driver is the only thing that knows when it is valid to move forward in the program. If you're reading data over SPI and you're still filling up the buffer, you can't just leave just because your coroutine got resumed. You need to, from this point, go back up, check to see if hardware is busy, and if it is, co-await again. This will suspend the coroutine until the next time it can execute. And I'll make this clear. Time is the only one that does not need a loop. All the other ones actually do need a loop of some sort. The other two are sync and external. Sync is very similar to I/O in a way. Usually if you're doing some sort of I/O where multiple different contexts could potentially try to use it, which I'm starting to realize might be the typical use case for most drivers, unless they're synchronous. But yeah, the most basic way to go about this is to check to see if the hardware is busy. If the hardware is busy, then some other context is probably already doing something and waiting for interrupt to wake it up. If your driver, and what your driver should do, is store a pointer to that context, and actually it says reference other, it should just be other, because other should just be a pointer. But you should call block by sync and then pass in the pointer to the current blocking context. This will tell that context who it's getting blocked by. And if the scheduler is sufficiently intelligent, it could create a hash map of sorts. This is a very crude way of going about this, but the simplest naive approach is to just create a hash map, where the key is the thing that's currently blocking other stuff, and the value is a list of your contexts that are waiting on that particular key to be finished. That's like one basic way to go about it. But from this, you continually wait until hardware is no longer busy. Once it's no longer busy, you can now pass through, set up the hardware. Now, this context now block on I/O. And any other contexts that come to call that driver's API will then get stuck in this loop. And all of them will pretty much get stuck in this loop until eventually they're resumed and the hardware is no longer busy. If you're all on one thread, then this will just properly synchronize together. If you're not on one thread, you'll need to use a mutex, but that mutex will need to wrap the driver's APIs. Yeah. And then finally, we have external. This is used when you are using a third-party coroutine, like standard task or something else like that. In those cases, you need to manually operate that coroutine. You're not allowed to co-await it unless you wrote the awaitable for it and had a way to make sure that if you resume the context, it properly resumes the external third-party coroutine all the way down. If you have an awaitable that can do that, then that's great. You can do that. You can await it. Otherwise, the appropriate thing to do when we don't have awaitable support is to just simply have the handle, the coroutine handle, or whatever object you have, check to see if it's done. If it's not, continually loop block by external. All right, so now we have operation stacking. This was a huge bug that has been really annoying me and freaking me out for a while. But I'm pretty happy to say that I came to a solution for this. So operation stacking used to be erroneous behavior that resulted in a memory leak and object lifetime violations. I want to explain this word erroneous behavior before I move on. Oopsie daisy. You may have heard of undefined behavior, UB. The C++ committee, I think a couple years back, at least 3 years ago, added into, I think it was 23, the concept of, or maybe it was 20, the concept of erroneous behavior. This is behavior that we know is wrong, is an error, is a design flaw and a typo in the code, and we're able to identify it to some degree, but we don't have an actual solution to it. If I'm remembering this correctly, we can define what the behavior is, even though we know it's an error. Things that, if you were to deadlock a mutex and you made it very clear in the code and the code could figure it out, that could be a thing. So this is erroneous behavior. We knew what it would do. We knew the behavior that it would commit. What it would do is you would have, let's say, foo loaded on here, and then you have bar loaded on here. These X's, these little circles, represent the no-op sentinel. The no-op sentinel is the coroutine handle that all contexts will use as like their null pointer as a way, in a way. We don't use no-op coroutine function because I discovered that is not required to return the same address every single time, which creates a bunch of funny problems. Yeah, so foo would have its continuation, meaning that where its return address is point to the no-op sentinel, which is correct. That's how it should be. Bar also has its continuation set to the no-op sentinel. The problem is that it should have its continuation pointing to foo. Now, when you do, and I should have explained what operation stacking is in the code. You have a context, you call foo, which is some coroutine, and you pass context to it. Then you call bar with the same context, and now it's kind of a question of what happens next. What happens next now is actually that now the continuation of the new coroutine promise is set to the previous active coroutine always. In more simpler speak, the way this gets stacked is that bar now points to foo, and if you put in like baz in here and you didn't start resumed any of these, then baz would point to bar would point to foo. When bar finishes, it'll say my continuation, the code you should run after me is foo0, is foo. And the 0 just represents the first function in the sequence of functions that eventually resolves this asynchronous operation. And the funny thing about this is that you can take any context at any point and just slap another coroutine on top of it. Not good for your memory usage, but you can basically just kind of halt a coroutine and then synchronize it against another coroutine and let it just kind of just go. And that's what happens here. So foo gets put in here, but once you put in bar, it must now serialize after bar. So bar has to complete first before foo can start. And this is a pretty obvious reason. If foo were to begin executing and somehow had its stack pointer over here and then moved it across, you'd destroy bar, which would be a lifetime violation because whatever objects that are in here didn't have the resources released. Even if you could skip ahead and put the extra data behind here, which can kind of work the way I have things done. I think I can come up with a way to make that work. It seems way more complicated and convoluted. Oh, and I wanted to explain one last thing, just so it's on the record and I have it somewhere online. I need to explain the object lifetime violation part because I remember when I noticed it for the first time, and that's what really got me even more concerned about this. A memory leak wasn't too scary for me because I was like, okay, well, what if we could just set the context's pointer back to the beginning? Should be trivially easy to do in code. And it would be fine so long as there weren't any object lifetimes that could be a problem. Well, there are. If I pass a string into foo will literally save a copy of that string inside of its parameter. Let's assume that it's a string value, not a string reference. If I can no longer access foo, I can never clean up those resources that string has allocated. I now have a resource leak. And I think I found this from the leak detector in GCC or LLVM, which is really cool. But that was where I realized that this is a really critical problem because you could pass a driver through, or maybe not a driver, but you could pass something through that's important, and now it's stuck. And the moment you try to destroy this thing is when you get full UB, because or you just get a full memory leak because you can't actually recover this space ever again. One funky thing about this, I don't know if I'm going to try to find a way around this because I think it's just potentially extra code to detect this. But if either one of these futures dies early, the entire context gets canceled. This has to do with some lifetime reasons. If you don't cancel all of them, it's kind of hard to determine which one to stop canceling on. My cancel function currently just runs until the active coroutine becomes the no-op sentinel. So it's just easier just to keep that loop the way it was before. Also cool thing is that if you resume future A or B, doesn't matter, bar will be resumed and it'll go down. And it's because of the fact that context has a single active coroutine, it's always the bottommost. So even if you ran something above it, future actually internally just calls resume on the context. It does not resume its own coroutine handle because that could be very dangerous. And the danger will be shown in this next slide. And we're almost done for the meeting, actually. This is the last slide, I believe. Cross-context footgun. I had a more extreme example where you pass the future in as a parameter. It would work the same way. It'd have the same problem. But if you had some additional context and you attempt to co-weight a coroutine using that context, you may or may not have a problem. You probably have a problem. So the following code is a problem. If you await these things, if the routine A, this little routine here, finishes without suspending and it's done, then everything works as fine. You get the value back, good to go. If routine A suspends and is unfinished, well, we have a bit of a problem. If you have a future that's somewhere out here that points to funct and you resume it, well, it's going to resume this point of the code. It's not going to resume the active coroutine. Or to be more clear, even if the active coroutine is routine A and you resume funct, which is currently pointing to routine A, if routine A awaits on something else, you will early resume routine A. What was happening to me before was that I was actually resuming funct, and because this thing wasn't finished, it would throw an exception. In this case, the default exception when you're in the wrong state is operation canceled, because there's no other way you should have gotten there rather than canceled. But in this case, you're able to get there early. So what I've done now is if you ever get in the situation, it currently invokes the contract violation handler or calls terminate. This one I'm waiting for 26 or a compiler where I can run 26 so I can actually use this and test it out. I don't like this at all, not at all. What I would prefer is if we could somehow route the future that the context that resumes this guy down into this so that nested context works. Because at that point, then you just run through this until this is done, then you return back the values. I would love that. I think that would be really neat to support that. The way you're supposed to support this, the way you're supposed to do this is actually to do block by external. If you have another coroutine, you're supposed to be a supervisor and you're supposed to resume it and check if it's done, then suspend yourself. You are not meant to directly co-weight it. But the problem is it seems like a thing that you can just do. It compiles and it can work in some particular edge cases. So right now it's really just about either just settling on terminate or contract violation handler, or I try to figure out a way to wire and chain these contexts together. I don't have a solution to that yet. And to be fair, I don't know if it's possible without a lot of overhead. And that's pretty much it for these slides today. But I want to go back and talk about this problem right here. Originally, I left this to be a erroneous behavior thing. Don't do it, right? I really, really, really hate APIs that give you footguns like this. Because, you'll look through the code and go, I see, this is why it didn't work out. It's because of this, I accidentally put, there was context 1 and 2, and I put 1 and 1 because I was copying and pasting things. It's too easy of a failure to have. I then thought about, what are the options for what we could do with operation stacking? What are the necessary behaviors for this? One idea, and I didn't know how to do this, but I was like, what if I could somehow detect that you have done something like this? What could I do? I could throw an exception, okay? I could terminate. I could do the stacking thing that I wanted to do. And I thought about the error handling option for this. And I thought, well, if I wasn't using exceptions, what would this look like? I like to think about that just because if I have any users that really, really care for not using exceptions, I want to know what the code would look like for them. And I kind of hated the idea because then I'd have to make, I think, the future type. No, I don't think that would work either, actually. There wasn't really a good, clean way to use result types for this per se. The APIs kind of get a little funky. I could make their state automatically be canceled so that if you try to get their value, you get canceled thrown at you. So that would still be exceptions. If I had another way, if I had made an expected or something like that, if I returned back an expected or an optional, then that could be like the thing. But I really didn't like the idea that if you just do this, just because we have this situation possible, I now must turn either each one of these into a check macro to do the propagation for you, or you have to do the propagation yourself by hand, or you have to wrap a try-catch around this. I hated all of those options equally, because even though I like exceptions, and I think people think I'm really into errors and throwing errors. I actually hate the idea of throwing errors. I actually hate the idea of propagating errors unless you know exactly how you intend your user to handle those errors. If you don't even have a modicum of idea of how an error is supposed to be handled, then unless you're just trying to explain that there is a bug, I feel like a contract assert or even just terminating or panicking are the right options. I think Rust has that a little bit better. I think they do it too much. I think they reach for panic way too often. But here's the thing that I think hopefully people watching this will think a lot really hard about when you're designing something. Think really hard about the consequences of your actions in your API design. I went back and forth with operation stacking for about, a month and a half, maybe 2 months actually, since I discovered that this was a problem. And I was never satisfied with any of the answers that had any sort of error handling or termination responsible for it. I actually do not like that this thing currently does a terminate and contract handler, blah, blah, blah. So I spent some time and figured out that I can actually set this guy when the future is created. So I can use the context's current active coroutine to set the continuation for the next one, rather than doing it during the await suspend time. I normally would grab it from await to suspend because that's basically saying, hey, I'm the caller. Here's my coroutine handle. I just skip that. I just say, here's my future. I have the context. I'll grab the continuation from there. This is basically zero cost because all I did was move the assignment from when you create the future from when you need to await the future, away from when you have to wait the future. This is amazing because now I got rid of all of the error cases. There are no ways to have errors with this. The only penalty you have is that your code is now serialized. Now you may wonder, okay, well, what if that's not what I wanted? Well, if it wasn't what you wanted, you shouldn't have typed it this way. But at the very least, your code should operate as intended. You just have it be serial now. It's no longer in parallel. But I think that's a beautiful way to do this. This is something that I'm going to recommend that people avoid at all costs. I don't think there's much reason for you to utilize operation stacking. I made it a first-class supported operation because the alternative was memory leaks and object lifetime violations, or better, but you throw an exception. But I want to make this clear again. If your API does not need to burden the caller with basically what you're doing is saying, I don't know how to handle this, you handle it. And then now that gets spread everywhere throughout your code. And even if you go just a little side note here, well, in my language or in this thing, it'll inline. I say, I don't care if it inlines. You still had to write the code to handle it. You still had to pawn off this work to someone else to manage. Even with exceptions, making it so you don't have to see all that stuff. You still have some point in the code that has to manage that. And if you don't have a way to properly manage the situation, because it's really just a bug, it's a problem with your code, with how we had it set before, all you're doing is really annoying your callers, annoying your developers, annoying your library users. So I behoove you, when possible, whenever you're writing APIs, to design them in such a way that it's nearly impossible to use them. Here's one little example. Block by time. If you try to resume a context or a future that is blocked by time, it doesn't do anything. It actually just doesn't do anything. The resume call actually checks to see if you're blocked by time and will skip calling resume on the context if that's the case. Same thing with the context resume function call. I believe it also checks that as well. And those should get in line with each other. But the point is that I just didn't like the idea of just getting random erroneous behavior because someone called resume in the wrong spot. I'd rather you call resume 100 times and then check some time stamp and go, oh, I need to unblock it. And then you unblock it and then you resume again. It's like somewhat degraded behavior. It's not like the best thing ever, but I think that throwing an error on the first sight of something that's slightly weird is sillier than simply having code that mostly just operates as intended and it's hard for you to mess up. So that that's all for me to say is that I'm actually pretty proud of where I've gotten with async context. Maybe other people won't like it as much, but I'm hoping at some point I can get rid of this problem. But this was one of those bigger issues that I'm really happy we fixed because now the library is harder to use incorrectly. Technically it's incorrect, but like it's safe. It's well-defined behavior. And that's pretty much it. That's my little rant. Talk to you guys in the next 2 weeks.